All right, so finishing up the chapter 8 lecture with basically the last section, which is split into a couple of parts called Earth's atmosphere. So we're going to finish off our discussion of the planet Earth, having started on the interior and finishing on the exterior. So when Earth first formed, it had this thing called the primary atmosphere, which we really don't think about very much, and we don't know anything about it in the sense of like there's no evidence of it. It's just a supposition, really. It's the idea, well, this had to be what was around because these elements are not only the building blocks of the universe. This is basically what existed after the Big Bang, which might seem like a bold statement, to relate to Earth. But literally, this is just, the basic building blocks of the universe. Everything else comes from stars. And it also was basically what the early solar system, that primordial solar system that we talked about in chapter 7 was composed of. When we talked about the stellar nebula and that collapsing into the disk, and then the protosun, popping up in the middle because of all the matter getting pulled in there by gravitational attraction, and then the leftovers forming the mini planetismals that eventually led to the solar system that we have. Well, when all those planetismals had crashed into each other and formed planets, there still was a bunch of leftover gas from that original stellar nebula that became that disk, right? The protoplanetary disk, as it's called. And the what that gas was composed of was hydrogen and helium. So that would have been abundant and so easily captured by any large gravitational body. So it is inevitable that Earth at some point had a hydrogen and helium atmosphere. And what's cool is we'll come back to this idea, which is one reason I wanted to spend a minute on it when we talk about the gas giants, because they ended up following a very different path of what happened to the early hydrogen and helium that they captured. But let's find out what happened with Earth. Okay? So we already know that hydrogen and helium have very small masses. They are the two lightest elements on the periodic table. And when we talk about hydrogen, we're talking about this diatomic gas of hydrogen, H2. So we're talking about the molecule of hydrogen with an atomic mass of 2 because it's two atoms, each with just one proton. And every nucleon has an atomic mass of 1. So that's what this number refers to. No kilograms, although we could convert it to kilograms, but instead, this is just the way we quantify and compare atomic masses. Helium doesn't end up in a molecule, and so we don't introduce one. We just kind of and the only reason we're introducing the hydrogen molecule is because it'd be really unrealistic to say that it's atomic hydrogen. So in the sake of realism and at the cost of a little bit of complexity, we say, okay, this is what hydrogen looked like. This was the atomic mass of the molecule. Atomic helium, gas on its own, noble gas, had an atomic mass of 4, even though it was just one atom. And that's because the nucleus of helium has 2 protons and 2 neutrons for a total of 4 nucleons, hence the 4. All right, so there we go. We got all of the H2 and He, right? So all of the hydrogen molecules and helium atoms were going around Earth, right? We're pulled around it, creating some sort of atmosphere, but a very short-lived one. Okay, so these gases that coalesced, gravitationally tugged to Earth, captured by Earth, came from the stellar nebula, as I said, all right? But they move very quickly. They are easy to accelerate. It doesn't take very much energy to cause atoms this small to speed up so fast that they can escape into space. As I said before, that means that they are reaching the escape velocity. Hold that thought because we're going to see it really clearly when we look at Mercury. There's a whole section where we introduce how to quantify the heat effects on a gas in an atmosphere, and that's the heat coming from the sun, and then how that gas can reach a certain speed that allows it to escape into space. And that's like, how you lose an atmosphere. And speaking of losing an atmosphere, as the picture implies, all these little arrows are kind of pointing up to where the word space is. The hydrogen and helium atmosphere that Earth had, that primary atmosphere, got lost into space. And we can kind of think of it maybe getting lost into space as the sun really, heated up, right? As the sun became as hot as it, was going to get when it reached its full operating temperature, that was the point where there was no chance of holding on to it. And also, it's not something that happened in an instant. You know, all these processes take some amount of time. Although I don't have a time scale on this one, I would be totally just guessing on exactly how long it would take. But it could have been, relatively fast. I'm not sure. So, regardless, that atmosphere just totally escaped. Nothing really would have been left behind. There would have been no opportunity for the hydrogen to say, like, you know, get like, stuck to the surface. It's not going to turn into a liquid. There's not going to be any hydrogen rain. It's way too hot. You're not going to turn hydrogen into a solid. That's very difficult to do. So no hydrogen snow, and same for the helium. So that's really there's nowhere for the gas to go, and that no other legacy it could follow, and it could have formed other molecules. Yeah, it could have bonded with things, and I don't think it did. Although if we look at what was outgassed, with the sulfur dioxide, nitrogen, um, maybe. Although no, I don't see anything that really points to that because even the nitrogen bonded with the hydrogen, there was some sort of splitting. Yeah, now I was just thinking out loud, but I don't know in other words, that if any of those gases would have, if they had been left behind, been able to interact with kind of the next gases that were introduced to finalize the secondary atmosphere. But regardless, lost. Okay. So now instead of having some hydrogen helium atmosphere, they would have no atmosphere. But that didn't last long because the planet, as it cooled, started to what's called outgas and just, have eruptions. All that heat that is now trapped underneath a solid crust of this cooling planet occasionally, reaches the surface. That's why we have plate tectonics and volcanoes and those ideas, those processes started early on and they started to release gases. Okay. And so we started to have H2O coming out in the form of, like steam, starting to introduce that, kind of a water cycle. And we also had outgassing of ammonia over here with the nitrogen and the hydrogen. So their carbon would have been coming out as well. I actually don't know exactly what would have been the outgassing of the carbon, but you had this, for whatever reason, general evolution into an atmosphere that looked like this. And it might seem unsatisfying that I'm like, oh, I'm not sure exactly where some of these gases came from, although we do see, that there was some trend of, H2O getting vaporized, and as I said, the ammonia. But what we will see in more details is where they all went and how they led to our current atmosphere. And that's more interesting, more relevant. I'm sure there is research about this secondary atmosphere, but it would be beyond the scope of the class. And this is an atmosphere that existed basically before there was any life. So that's the way I think about it. I think it's a pretty clear division that this was not the first, right? But still a very early atmosphere of our planet and one before any life had evolved. So like as soon as the first single cellular organisms, these like kind of, like prokaryotic little tiny life forms started to pop up, they started to change the atmosphere and then, their descendants started to live in a very different atmosphere that changed over the eons. But at some point, this would have been what would have been around the Earth. It would have been mostly water. Okay, so we would have had a atmosphere mostly composed of water vapor at 58%. So that's kind of a strange thing to think of, right? To have an atmosphere that is just like mostly, water vapor. There would have been carbon dioxide in significant amounts. And I keep actually wanting to see what the exact chemical process is because this obviously creating carbon dioxide happens really easily on terrestrial planets. When we look at Venus, when we look at Mars, there's a huge amount of carbon dioxide in proportionally at least in both of those atmospheres. And so obviously like it's just this baseline default gas that gets produced. And probably from like some sort of like maybe photon rock reaction that it's just really easy for carbon dioxide to get produced somehow. And it's a heavy enough molecule, unlike the hydrogen and the helium, where it can get retained in an orbit like Earth's. And the reason I mentioned orbit is because orbit relates to distance from the sun. Distance from the sun really relates to intensity of the sunlight. And that's what really matters when we talk about atmospheric retention. It's like how hot is the sunlight that's hitting that planet? Because if it's too hot, then you lose particular gases. And so, here we're not losing the carbon dioxide. We're able to hold on to it. Sulfur dioxide was getting produced as well and was a particular, or a significant proportion of the atmosphere. Nitrogen probably split apart from the ammonia that was outgassed. And what I mean by that is that the N would have been split off from the H3, so that larger ammonia molecule could get broken apart. Plenty of ways to do that, one being X-rays, coming from the sun. And noble gases, not interestingly, not sure about the source, but I can reason that it would probably be some just basically outgassing from the cooling planet because I know that there are huge reserves of helium underground that basically are bubbles that have gotten created as the planet has cooled. Well, I'm sure those make their way to the surface and get released. So there's these noble gases that just aren't going to bond with anything, stay as a gas, and so they kind of percolate their way to the surface and then become part of the atmosphere. And with the exception of helium, your other noble gases, your neon, your xenon are going to be heavy enough that they're easy to hold onto, not to escape into space. All right, so ended up with this inimical to life atmosphere, but kind of interesting, that has a lot of water in it. Okay, now our current atmosphere looks totally different. Instead of being over half water, it's about 80% nitrogen. It's 21% oxygen. Where did the oxygen come from? The noble gases are still 1%. Carbon dioxide is tiny at, less than a 20th of a percent, right? Well, not a 20th of a percent, but well, actually, I guess it is a 20th. Yeah. Yep. Less than a 20th of a percent. Water at less than a half a percent, and sulfur dioxide at a thousandth of 1%. Okay, actually a 10,000th of 1%. So tiny amount of sulfur dioxide. Okay, so how did all these changes come about? Right, and here we see, current atmosphere has some water in it that is going to be the clouds, right? But not proportionally a large amount. We have oxygen taking two forms, one of them being diatomic oxygen. This is what we think of when we actually think of oxygen because this is the oxygen we breathe. We also have O3, which is ozone. Okay, so that contributes to the overall 21%. We don't breathe ozone, but it is important component of our atmosphere because it's able to absorb UV rays. So we want to have an ozone layer. We've got the carbon dioxide, all right, the byproduct of respiration of oxygen, dependent life forms. And we've got all this nitrogen that is taken the form of diatomic nitrogen because there's a clear trend here that a lot of these lighter elements, these lighter atoms, have stable molecules where there's just two of them. All right, so it is true of hydrogen, it's true of oxygen, and also nitrogen. All right, so that's diatomic nitrogen. And yeah, I already mentioned the water, but I'll go ahead and circle it. Okay, clouds. Is there water in the atmosphere that's not clouds? Yeah, kind of, but mostly we think it's probably composed of the clouds, as far as I know. All right, so this now has them side by side because we're going to talk about the evolution. How do we go from this secondary atmosphere with its composition to the current atmosphere. So what happened to the water? So I think we talked about this, and I'm going to give it away, even if we didn't. It condensed, okay, into a liquid, because it could have, condensed, so to speak, or frozen into a ice, but mostly it turned into a liquid, and that's because the effects of the atmosphere were made it so that the planet was cooler and that water wasn't naturally in the vapor state. So, and there's an ocean, right? So what we had is water changing phase, changing from vapor into a liquid, some of it turning into an ice because the poles supported, that phase. It was cold enough to have, big reserves of solid water. And to do that, the planet had to cool. And it wasn't just cooling because of the surface, although perhaps that had something to do with it, right? Having a molten planet underneath, right? But the planet was already not molten on its surface when, we talked about the secondary atmosphere, although there may have been more heat still coming out. It's not a steady process, although it's, a gradual process, the cooling of planets. But more importantly, the atmosphere itself and its gradual changes allowed for a different, blanket effect from that atmosphere. So as the atmosphere changed, it allowed the planet to become cooler. It was able to absorb more of the sunlight in the upper atmosphere and keep the surface cooler, and therefore facilitate the phase change of water from vapor to liquid. All right. So having this much water in the atmosphere really tells us that we have a very hot world, right? To have that, and if you have this much water in your atmosphere as a planet in general, if you're looking at other planets or, kind of when we talk about the evolution of Venus, that's going to be a planet that is doesn't have liquid oceans, so it's just it's an extremely hot planet, right? No ability to have life living in water on the surface because it's just, too hot for the water to ever, actually become a lake or an ocean. But Earth cooled, we got our oceans, and we lost most of the water in the atmosphere. It's a good thing we still have some because, like I said, we have a water cycle where, the clouds, like recycle that water, bring it up in the sky, move it to other areas. We have rain, watersheds, that flow of nutrients that is facilitated by that water cycle. So crucial that we still have water in the atmosphere, but it's a tiny portion of it, right? Most of it's in the oceans and the lakes and all that. Well, mostly in the oceans. So what about the CO2, right? Because there was a huge amount of carbon dioxide initially. Mars and Venus still have mostly carbon dioxide atmospheres. Why did Earth lose its? One is because the atmosphere, the atmosphere facilitated that relatively cool surface of the planet, and that allowed for CO2 to get locked in the ocean, right? Because now, we had oceans, we had liquid water, and so the CO2 could get absorbed by water. The water then, through mineral processes, could then deposit that CO2 into certain rocks, and then those rocks could, move along because of tectonics, right? On an oceanic plate, they could get subducted under a continental plate, and your CO2 is then locked into the crust of the planet. All right. And that's happening primarily because of the abundance of liquid water. Right. So some CO2 can get just absorbed into, minerals and other processes, but water is going to make it happen, right, more readily. The other place where the CO2 in the atmosphere went was into the burgeoning life forms on the surface. As life evolved to use CO2, well, it used it. And in that process, it absorbed it, it used it in its structure, right? It converted that CO2 into, parts of it. It's like, its cellular structure, and later it's, its overall macroorganismic structure, things like, like the bark and the leaves of plants. And those organisms that were able to evolve to take advantage of CO2 were, by just a happenstance of chemistry, doing that with a chemical chain, a metabolic chain that involved an output of oxygen. So that was just the most successful way of using CO2 as an energy source, which I think of as like, okay, well, hey, there's a bunch of CO2 around this primordial soup organism that just sort of like pops up as this self-replicating molecule. Well, the one that's going to survive is the one that's taking advantage of the abundant, you know, complex um, molecule that has carbon in it, right? This carbon atom, which is so versatile and can lead to carbon-based life, so that's kind of the whole story is that CO2 was around, life was able to take advantage of it and make what we know as carbon-based life. And carbon really is this special atom. The way it can create so many different types of bonds. And but just like I said, that metabolic process that was able to take advantage of the food source that happened to be around, and food source in a real general case, because it's like, oh, you're eating CO2? Well, kind of, right? And you're just pooping out, to be a little crass, excuse me, oxygen, right? That's just the byproduct of the plants. So it wasn't like there's no advantage on its own to produce oxygen. It was just the best way to use the CO2. Interestingly, a whole other set of organisms started to, randomly mutate to take advantage of that oxygen. And of course, as there was more oxygen around, it became another available source, right? Of a molecule that life could take advantage of. So all of the oxygen breathing organisms came after the CO2 breathing organisms because they're like, hey, there's this waste product from all the plants. How can we use it? Well, animals have, right? So do we as humans, and so do dinosaurs, shown here in the picture. Okay, but that's all fun, but how does it relate to the CO2 itself and the CO2 coming out of the atmosphere? Well, if the plants are eating it, then it's coming out of the atmosphere, right? But how does it stay out of the atmosphere? Well, it stays out of the atmosphere because when the plants absorb the CO2 and they use it to build their bodies, well, then when the plant dies, it stays with that dead body, right? Think about, a dead tree. Think about all these small dead bacteria, all these the plankton, all these organisms and all these different epochs of the life on Earth have gone through their life cycles, absorbed CO2, and their bodies have been left behind. They've sunk to the bottom of oceans if they were ocean-dwelling organisms. They've littered the surface of the planet if they were land-dwelling organisms. And the plants that ate the animals that ate the plants, not the plants that ate the plants, but the animals that ate the plants also died, and the CO2 in their bodies would have that got trapped in the ground. And in the way that they got trapped in the ground is they became certain minerals, right? We have lots of rock types that are based off of organisms like limestone, for example. Obviously, when we talk about fossil fuels, where those are the pressurized and liquefied carcasses of tons and tons of life forms from previous eras. And so that's all the ways that CO2 became part of the the ground, right? The crust, the upper crust, instead of being in the atmosphere. And so you see that trend, right? There's always these opportunities to both, release gases into the atmosphere, but then to pull it back into the crust, right? In some sort of chemically driven process. Okay, so we know that the carbon dioxide was absorbed both without life and with it. Okay, and I don't know what the breakdown is. I was thinking that, like, could we say that, that life, like, absorbed the vast majority of CO2, or was it the oceans? But I'm not sure. The sulfur dioxide was absorbed by the water, so that there wasn't a life really taking advantage of the sulfur dioxide, and instead it was just going into the oceans. But the fact we had the oceans because the water had condensed was crucial to the sulfur dioxide leaving the atmosphere. So SO2, right out of the atmosphere into the oceans. Also made its way into rock layers, got deposited in mineral processes. So the sulfur dioxide was absorbed, leaving almost nothing behind. Okay. Nitrogen just survived. So we go from nitrogen being 5% of the original atmosphere to being 78% of the original atmosphere just because it never got used. There wasn't some sort, it wasn't absorbed by the water, right? It was not part of life. Life never took advantage of nitrogen. Nitrogen is often described as this sort of inert molecule. Like N2 isn't isn't used in a lot of important chemical processes, both, inorganic and organic. And so it's always just kind of there along for the ride. And so now it makes up most of our atmosphere, but it doesn't, it's crucial for, the pressure, right? So it certainly serves a purpose physically, but it doesn't really serve a purpose, chemically. And maybe some, the cheerleading squad of nitrogen might tell me that I'm full of it and say, hey, no, no, nitrogen does do some things, but I've never heard of them, and we can even just see that it just stuck around, right? Not involved in any processes. The fact that it went from 5% to 78 might seem confusing, but it's just because our current atmosphere just has a lot less in it. It's much lower density than the secondary atmosphere. So this 5% of, this really heavy, very packed full of atoms atmosphere that existed before there was life, maybe during the first 500 million years of Earth. Well, now, right, it's that 5% becomes 78 because the current atmosphere is just much thinner. Kind of feels weird to call Earth's atmosphere thin, because compared to like Mars, it's quite thick. Compared to, the non-existent atmospheres of, the Moon and Mercury, it's dramatically thick. But, it is really thin compared to Venus's atmosphere. So that's kind of what comes to mind for me is that, that secondary atmosphere is almost more like like Venus is today, although also different in some crucial ways, especially chemically. Um, but still, the thickness would have been comparable. And, so that it would have been like just really, really high pressure if you were on the surface of that secondary atmosphere. Like almost like being at the bottom of the ocean, right? Humans wouldn't be able to survive under such high pressure. But today, we have this relatively lower pressure that, we're used to. Noble gases actually just also stuck around for the ride, which also totally makes sense. They don't their chemical structure, if you're familiar with it, has these full outer shells, which is the terminology for how electrons work, and chemical processes are always about those outer shells. And so then it means that they can't bond with anything. There's no way that they can form a bond, just none. So that's why they're noble because they're sort of aloof, right? They don't interact with other chemicals or even other atoms. All right. So then it begs the question, if you've been following along, that, we got one last arrow that is, not described, right? We showed everything else, but that just showed where everything went. But there was one new, atom, one new molecule, diatomic oxygen, as well as the ozone. And where the heck did it come from? Well, as we said, it came from plants, right? So plants produced it. So that's where oxygen came from. And I know I briefly mentioned this last time because it was one of the first, kind of key ideas is that there's no process that produces oxygen that scientists know of other than photosynthesis, in other words, other than life. So that idea of having free oxygen in the atmosphere, we don't see it anywhere else in the solar system, and we don't know of it existing on any other world. We have it here on Earth because of plants. Okay. Sure, trees absolutely produce it. The majority has been, and I think always has been since, as life evolved, plankton and algae in the oceans produce the majority of oxygen. They're the primary drivers of oxygen in the atmosphere. And it's the second most common molecule in the atmosphere, 21%. Although that's lower than most people will say if you ask them. If you ask someone like what's the most common molecule in the atmosphere, or what's the atmosphere made out of, they'd guess oxygen because they know that we breathe it, right? Not thinking that, that it's nearly 80% nitrogen, but which we don't breathe and, but also doesn't hurt us. But, the oxygen is, it's a big chunk, right? And it's it is interesting. I'll just like point this out because I love people to think about this, although I won't belabor the point that at 21%, it's like, okay, well, that we need that, right? We gotta breathe, and we talk about, climate change and how we're changing the amount of CO2 in the atmosphere. Well, are we in danger of, this oxygen level going down, right? Because essentially, we're releasing a bunch of extra CO2 that it can, that CO2 can drive chemical bonds to, grab oxygen out of the air and turn it into other molecules. So, could we have a world where something that we're doing to the atmosphere actually starts lowering the oxygen amount? And it's not unfathomable. And people do monitor the oxygen, make sure that it isn't changing. They consider it in their models of climate change and atmospheric changes. But what I've read is that there's nothing to suggest that it's like a real concern, that we're not going to, run out of oxygen and not be able to breathe. But that would certainly be, the the worst way for humans to cause their own extinction, right? Would be to, somehow cause an atmospheric change that significantly removes the oxygen, and all of a sudden we can't breathe our own air. But for now, we are good. Okay? So what despite that statement of being okay, so we're not going to literally suffocate the world by somehow, removing the oxygen as far as we can tell. There are some major things that are happening with CO2. And it's interesting too, because it's such a small amount, right? And so just changing that tiny proportion of carbon dioxide in the atmosphere obviously has a big effect. So when we talk about the, CO2 driven, the greenhouse gas driven climate change, we're talking about just tiny changes in the amount of carbon dioxide, because it turns out that that's all it takes to cause significant temperature changes. Okay? So these next slides do a good job of explaining why a temperature change is associated with a greenhouse gas. So let's run through them. Now, to do that, we've got to define the difference between weather and climate. Sorry if you've already seen this. It's a common, comparison or common statement that climate is the long-term average of weather. And every science book likes to say this because the ideas are commonly confused. People say, "Hey, how could the climate be getting warmer if this winter is so cold, right?" And it's because random variation does not represent a trend. So weather is just random variation, and it can be really random, right? And you have to look at a pretty large time scale. You have to look over decades, many years, and many locations, because weather is regional, and even closer than that, right? It's just like you zoom down to a few square miles. So that's not going to represent the actual, you know, trend of data. It's not climate. They're just not the same thing. Climate is what you expect, right? It's a prediction, it's a model. Weather is what you get because it's the random variation in the system. What is sometimes called the noise of the system, because it's just all these events that have too many variables to predict accurately. And in this graph here, you could actually think of the climate as being the average of the slope, okay? And this is showing on the vertical axis the temperature, and the temperature varied off of some common baseline, which was the baseline prior to 1980. And then that's so okay. So the climate would be like if I took an average and I drew a straight line right through, right? That's the climate change. But then the weather are all of the actual up and downs, the jumps around that average. All right. So with that out of the way, what the heck is equilibrium temperature? Okay. So the key thing to understand in everything we're just about to talk about is actually really surprisingly hard to accept, not because it's like it seems wrong, but it seems too simple. And it's that the incoming and outgoing energy are balanced at the equilibrium temperature. Okay. So any object will reach a temperature so that its outgoing and incoming energy are the same. And this is true of like everyday objects and just, like around you, right? Like I'm trying to think of the best analogy. That's why I kind of paused there because there are some good ones, right? But so okay, we think of temperature, right? It changes throughout the day. So you know, is there an equilibrium temperature? Sometimes we're always in a state of change, right? It's like, things are heating up in the morning, they're cooling off in the evening if they're outdoors. You know, if you're heating something up on the stove, then you just kind of like heat it up and then you let it cool, right? But if you think of something sort of just like sitting in a room, where that room is the same temperature for many hours, and then you can start to get a better idea of things stabilizing. And you can start to get an intuition that every object does tend towards stabilization. And this is really a physical fact that, and if it doesn't seem right, you just have to take my word for it, that everything is going to move in a direction of stabilization. And in this case, we mean moving in the direction of equilibrium temperature. If I leave my hot, freshly baked pie out in the kitchen, and the kitchen temperature is the same for the whole afternoon, then that pie is gonna cool down until it reaches the same temperature as everything around it. And then it will stop cooling. Because at that point, and why does it stop cooling? Because at that point, it's releasing as much energy as it's receiving. And so it has done something to return itself to equilibrium with its environment. And what it did is it initially released a bunch of energy. It was initially really hot. It was heating up the air around it, causing convection, hot air rising and moving away from it. It was conducting heat into whatever it was sitting on, right? This hot pie. It was also radiating heat. If you looked at it with a infrared goggle set, you would see it glowing hotter than everything around it. But as it cooled, all of those processes of letting it cool got it down until it was at an equilibrium temperature. And once it was there, it was still absorbing energy. It had to be, right? Because it's still in a room, it's still getting hit by light, it's still, in contact with objects around it, so it's still got energy coming in. And it's still, if you looked at it infrared, it would still be glowing, but it would just be glowing in the same infrared wavelength as everything around it. So that means that it's then in a state of energy in, energy out. That never stops. But now that it's at an equilibrium temperature, that energy in and energy out are balanced. Okay, so it's one of that introduction because we'll see it in pictures here. So the Earth is in equilibrium. The amount of incoming energy via sunlight has to equal the outgoing heat from long wave infrared radiation, because the Earth has had plenty of time to reach equilibrium, right? It's been sitting in space for quite a while, and the sun hasn't significantly changed for billions of years. So it is absolutely in equilibrium. The amount of energy coming in equals the energy going out at any point, averaged over any period of time. Okay? So with that, all we have to think about is how does it maintain that energy balance? Because as long as we stick to that idea that the Earth has to be in an energy balance, then we just need the mechanisms that facilitate that energy balance. And this picture has a lot going on. I won't talk about every little part of it, but it's showing the incoming light and the outgoing, also light, right? But incoming visible light, outgoing infrared radiation, and just all the different ways that you can split up those two processes and explain the energy budget. Neat diagram, lots of details, but not something we need to dive into right now. This was the cover image, if you remember, and this is just the carbon dioxide level going up. This matters because carbon dioxide is a greenhouse gas. Okay, why does that matter so much? Well, you'll see. Okay, greenhouse effect. You can look at it. It's a surprisingly effective way that just a few molecules of carbon dioxide, as well as a few other molecules, are able to trap a lot of the infrared radiation. Okay, so to start to kind of touch on the idea. So it turns out that you just need a few of these particular molecules, CO2 included, to be able to trap a good amount of heat via infrared radiation scattering reflection. Right, so the budget, right? So light comes in, incoming sunlight hits Earth. This is Earth's atmosphere shown in the light blue, not to scale. Okay, and then Earth releases infrared light, okay, radiated back out into space. As we know, those two totals, the total from the infrared light radiated back into space and the incoming sunlight from the sun, have to equal each other. So we have the energy into Earth equaling the energy out. Okay, so if the Earth just had the sunlight hitting and it was glowing, then these would be the only two things to consider: sunlight hitting Earth and infrared light radiated by Earth. And they would just be equal to each other. And the reason that we went from the top equation, energy in to energy out, to sunlight hitting Earth equals infrared light radiated by, is because we went from like the basic concept that energy is balanced to the mechanism that balances it. But obviously, we're going to introduce some other mechanisms because we've left space to do so, which is why there's a weird amount of space between the equal sign. Okay? But there are worlds that are like this. If you just had like the moon, for example, no atmosphere, just the rocks just glow. That's the only way for the moon to maintain an energy balance. Okay, so that would be the energy flux. That's just the joules per square meter, which we talked about when we talked about, the seasons. And the variable to consider for infrared is temperature. Now, we could just put energy flux again, just have, the infrared, but that wouldn't tell us anything because it would literally just be the same. Instead, we've decided to define the infrared by a different variable. And the reason we can do that is because of Wien's law. Wien's law was that relationship that told us that there was a direct, equation that related black body radiation to temperature. So that's why we can introduce this variable, this measurable variable, and this dependent variable, as we'll see, into this energy balance equation. So if Earth absorbs more light from the sun, it gets hotter. What happens to the infrared light the Earth emits? Now I'm just going to go over these answers because I want to get through the content. Okay, so more, right? Because they have to balance, right? If one goes up, the other has to go up because there's literally just two things, one on each side of the equal sign. What that would look like is this, right? The arrow represents an increase. So if sunlight hitting the Earth increases, so must the infrared light. Okay? Otherwise, the energy balance wouldn't be maintained. And that means that the temperature would have to go up. The sun all of a sudden became brighter, then your planet that can only radiate heat, by its rocky surface getting hotter would get hotter, right? There you go. Makes sense, right? But we have an atmosphere. So Earth can do more than just radiate heat by glowing. It's not just a rock in space. So the atmosphere introduces some extra effects, some extra things that can happen. The first one of them is reflected sunlight. Interestingly, this actually doesn't depend on the atmosphere. You can have reflected sunlight from a rock if your rock is, white or shiny. And so that, you can absolutely bounce some of the energy right back into space instead of absorbing it, glowing red, or infrared, and then emitting it that way. So, reflection, rocks can do it, but so can atmospheres. Okay? So in winter, white snow reflects more light off the Earth instead of absorbing it. What would happen to the infrared light the Earth emits? And I won't check for answers in chat, but I will give you a second if you want to try to answer it. So think about that. So in winter, white snow reflects more light. So what we're saying is that this went up. So if the reflected sunlight increases, what must happen to this term over on the right-hand side of the equal sign? Is there less of it, no change to it, or more of it? Less, because the reflected sunlight is subtracted from the incoming sunlight, because after all, it just bounces right away, right back the way it came. So if your reflected sunlight increases, that means the sum of the two terms on the left-hand side of the equal sign is less. Therefore, to keep the equation balanced, the value on the right has to be smaller. Okay? And that means the temperature would go down. So having snow cover the Earth brings the temperature of the Earth down. That's actually why at some points, hundreds of millions of years ago, the Earth has had not just ice ages like people talk about, which happened tens of thousands of years ago. Well, hundreds. The most recent one was 100,000 years ago, the most recent ice age. But But if you go back further, you can find these crazy ice ages. One of them called Snowball Earth, where you had this runaway effect where the more snow that covered Earth meant that the more reflective Earth became, and then it became even colder. So then there was even more snow until the whole planet was just totally covered in snow. All right. And it took some sort of like disruption to kind of like get it back going, some other energy input. Now, on to greenhouse. Okay. The greenhouse effect, the one thing we haven't introduced. Okay. So, greenhouse gases are particular gases that absorb infrared light very well, right? And they include carbon monoxide, carbon dioxide, methane, water, right? So, if you have a lot of water in the atmosphere, that would mean hot planet, nitrogen dioxide, and ozone. Okay, ozone is actually the one of the least effective of the greenhouse gases, and does more in terms of its absorbing of incoming I said not infrared, ultraviolet, the other one. All right. So, by the way, the reflection was the orange arrow in terms of the diagram here. And so now that we're going to introduce the greenhouse effect, we're going to go from a non-greenhouse atmosphere, one where there's little CO2 or any other greenhouse gas, to one like we have more of recently, in the last few decades, which is a atmosphere with lots of CO2 comparatively. And that type of atmosphere traps infrared radiation. Okay, it's basically reflected back down to the surface. All right. And so that means that our energy balance now has four terms. Still energy in equals energy out. But we got sunlight hitting Earth, reflected sunlight. Okay. We've got the infrared light radiated back out according to black body radiation. And we've got the infrared radiation trapped according to the greenhouse effect. A reflected light is called albedo. So if you have a high albedo surface, that means that it's highly reflective. So that's the term, the scientific term given to the level of how reflective something is. And then the variable for infrared radiation is how much greenhouse gas you have. So this would be the measurable value that could directly relate to this mechanism that, of course, relates to this energy. So if more energy in than out, then the temperature increases. So you might think, wait, isn't this violating the whole energy balance? Well, this is just temporary, right? So this is a temporary disruption. So to return to equilibrium, right, if your energy in goes up, in order to get back to equilibrium, your temperature has to increase. Okay? This causes more energy loss by the emitted infrared light. This continues until the energy output grows to equal the energy input, right? So you can disrupt that equilibrium, but it just means that things will change and you'll start returning to it, right? So every system seeks equilibrium and sometimes how it's described. If more energy out than in, the temperature decreases. This causes and this temperature on the planet causing less energy loss by the emitted infrared light, and this will continue until the energy output drops enough to equal the input energy, right? Again, return to equilibrium. All right, so this is just going to show everything we just talked about, but with an actual scale, right? So if you have an unbalance with sunlight, the sun suddenly became brighter, that means the energy in has to go up. Well, the one way to compensate for that would be to have more reflection, or rather, this is just showing unbalances. Sorry. So this is to say, okay, if you disrupt the system by suddenly making the sunlight brighter, then this is what it looked like. If you disrupted the system by suddenly having more reflection, right? So if the Earth just suddenly gets covered in snow, then the scale would tip down on the left. If you disrupted the system by having the infrared light radiated by Earth go up because something independently caused that to happen, right? It's kind of a hard one to have independently happen, but just like it could be that the Earth just starts like having energy come from inside of it, right? So, suddenly there's like more lava on the surface that could make a difference. All right. But one that can happen independently is the infrared radiation trapped in the atmosphere because you've changed the concentration of the greenhouse gases that cause that, the tipping of the scale down on the right. And so when everything is in balance, all four of those scale tipping, mechanisms would look like this, right? Keeping the scale flat because it's keeping the energy balanced. Okay. But what is climate change? Climate change is an increase in the CO2. So it's I say independent, right? So it's like you're not changing sunlight, you're not changing albedo, you're not changing the infrared radiation, not yet at least, right? So if you just change one thing by just introducing these particular molecules, these greenhouse gases, right? In particular CO2, this would be what would happen. You would just make this arrow bigger. All of a sudden, you have more energy staying in the system. Well, if you have more energy staying in the system, your energy outside of your teeter-totter, your scale is going to tip down, right? But we know that that's unsustainable. Earth is going to want to return to equilibrium. So that the only way for it to do that, other than, changing the albedo, right, changing the reflectiveness of the planet, is going to have the temperature go up. Because we certainly can't change the sunlight, right? There's no way that, like some effect on Earth is going to cause the sun to change. So we can definitely rule that out. So that means that the planet heats up until you get back to balance. So that's what's happening, is that we just have a warming planet in order to return to an equilibrium. All right. So what happens to the temperature of the Earth as its albedo increases? For comparison, it would go down, right? And so then this one just shows some more disruptions. So this is like shows the relationship between albedo and temperature. I going real fast to these because we've said most of what I want to say, and I'll just summarize it at the end. This would be like if you just changed the albedo and nothing else. So in the same way that we had that individual change. Hey, let's just introduce CO2. Good idea, right? Well, what if we just make the Earth shinier? Increase its albedo. Well, if we just did that, nothing else, the way that it would balance out is the Earth would just get colder. The temperature would go down, right? Assuming that we made no change to the atmosphere. Okay. Right? So if Earth moved closer to the sun, right? That'd be a change, right? If Earth moved closer to the sun, then the flux would go up, right? So if you just changed the flux, right, and nothing else, suddenly our orbit changed. That's not likely to happen. Or the sun just suddenly became hotter, also not likely to happen anytime soon. Well, then, the only thing that changed is the flux. How would that get balanced? Well, the easiest thing to change, the thing that will change with sort of the direct cause and effect would be the Earth would get hotter, and so therefore, more infrared to balance things out. And then here's your summary. More energy in than out leads to higher temperatures, and that means more infrared light created to release. More energy escaping than entering leads to lower temperatures, and thus less infrared light created to escape into space. So whenever you have an unbalance, the Earth adjusts and rebalances. So in this case, the unbalance is the introduction of a particular molecule. The climate change we talk about is the adjustment. The rebalance hasn't happened yet. And there you go.